So hi, welcome everybody to Visualization Day. My name is Joe Insley. I'm from Argonne National Lab. Here's a little rundown of, we have a pretty packed day for you today. So there's a handful of us from Argonne. We'll do some introduction stuff, general biz stuff. We're lucky enough to have experts from three of the more popular tools that are used in our field. Representatives from and developers of each of those applications are going to come and talk to you, do some presentation, some hands-on stuff. And then near the end of the day, we have some new stuff that we're exploring with looking at visualization using Jupyter notebooks. And then wrapping up the day at the end with the dinner talk. Bobby Kasturi will be here, we hope. He always gives a great talk, so you're in for a treat there. So just to get this started, I'm going to give an overview of introduction of visualization before we dive into some of the specific tools. So here's kind of the plan. I'm going to give some examples of visualizations, maybe hopefully tie this back into some of the science that you guys are working on and see some examples of how you can bring visualization into your own field. Talk a little bit about some visualization resources in terms of large-scale resources. Talk a little bit about visualization tools and formats. Go through some different types of representations. A little bit about annotation, movie creation, some minutiae there. Talk a little bit about, a couple of examples of often visualization is not necessarily the end product. You use it along the way for debugging and diagnostics, that sort of thing. And then I'm going to have Silvio Rizzi, who I don't see quite yet, but for the last section of the talk, talk about some new advances in the space of in situ visualization, and I'll let him talk a little bit more about what that is if you're not familiar. So I'll just start with some examples. So this is from a project, collaboration that I've been working on off and on for probably 10 years or more, looking at multi-scale simulation and visualization. It's an example of arterial blood flow. In this particular example, what they're interested in is looking at sort of what's happening in this area here. So what we're looking at is arteries in the brain reconstructed from real patient MRI data. And in particular, they're interested in this aneurysm that's formed on one of the walls of one of those arteries. As you can imagine, that if this aneurysm were to burst, that could be catastrophic. So they're interested in what's happening in this small subregion on the end of the aneurysm. So one of the reasons why, sort of feel this is an important example is looking at this multi-scale aspect, right? So they're coupling some fluid flow dynamics that's happening in the large scale in this overall flow in the artery, and you can see these swirly lines kind of showing the overall flow. And they want to understand how that impacts particle buildup on the wall of the aneurysm. And so that's done with a second code that's a particle dynamics code. And to give you an idea of some of the scale, when the simulation first ran, it ran on Intrepid, which was our previous supercomputer at Argonne. The fluid dynamics ran on one rack of the machine, so about 17,000 processes. And the small subregion at the end here that looked at this particle dynamics ran on 31 racks of the machine, right? So at that scale, there's not enough compute power to do that level of detail in the particle dynamics in the entire system, right? So it was important to be able to couple these two different scales together so the two codes talk to each other. And then in turn, it was important to be able to visualize the results of those two different, very drastically different scale simulations together. This is an example of climate. So a number of different models that were coupled, different climate models coupled together, looking at, in this case, The variable we're looking at here is total precipitable water, essentially the amount of moisture in the atmosphere. And so you can see where there's some tropical storms that have formed there. And so in this case, they started with observed data. So they took observed data, plugged it into their models, and ran their models forward. Then they're able to go back and compare the results of their simulations with the observed data, see how close they are, make adjustments, and whatnot. So that's another example. Here's an example where we were working at Argonne with, we have a number of corporate sponsors or partners. This is an example from GE, who makes jet engines. And so this is an example of where they're looking at reducing noise from jet engines, different types of nozzle that they can use. So another fluid dynamics type calculation. Materials and molecular science. Lots of, a few examples here of those types of simulations, and also collected data. So looking at different types of representations, some which are more domain specific, and I'll talk about some of the tools for a lot of these that go into a lot of these too. This is an example of cosmology. So this is a simulation of dark matter, evolution of the universe. And so where the bright areas are, where there's clusters of galaxies that are forming. And this is a particle simulation. So they're simulating on the order of 1 trillion particles here. We're looking at just a small subset of them in this particular image, but so looking at different ways to represent some of this data, and just going to give you an idea of some of the different types of, how to relate some visualizations back to the science codes. So taking a look at resources. So you might be familiar now with Cooley. I think you guys have most of you, I think, have run some stuff on Cooley, probably doing more computational stuff, but it's actually, we use it primarily as an analysis and visualization cluster. So it has 126 nodes, each with lots of memory, 384 gigabytes of RAM per node, some high, medium end processors now, and a couple high-end graphics cards. So one of the things that's important about this system for us is that it shares a file system with Mira, the compute resource. Right, so I alluded to before, we talked a little bit, we're going to talk more later about in situ visualization and analysis, where you start looking at trying to do visualization and analysis on the data while it's still in memory on the compute resource, because the gap is widening, right, between the rate at which you can calculate data and the rate at which you can write it to disk. So in the end, you end up, there's no way to save all the data that you're computing, so the in situ stuff is starting to look at how to do visit analysis on the data while it's still in memory, so that you get more science out of the data that you're calculating. You don't have to throw it all away. And so Cooley is a resource that we could potentially tap in for doing that. It has a high-speed interconnect between the compute resource and the viz resource, and again, it mounts the same file system. So if you do need to do, and primarily right now, the vast majority of visualization and analysis is done post hoc. So you do need to save data to disk, but at least in this case, you don't need to transfer data long area, across the wide area. We have a visualization resource that sits right next to the compute resource to help enable that. All right, so a look at some of the visualization tools and some data formats. So there's all sorts of tools, and these go from sort of integrated general purpose visualization applications, such as Visit and ParaView, and you'll hear much more about those today. Those are both open source tools. Insight is another commercial product that does much of the same thing. Some domain-specific tools, VMD, you'll hear a bunch about today. John Stone, the main developer from VMD, is here today to talk about that. And then there's also APIs, like VTK for doing visualization, ITK for segmentation and registration. So for building up your own tools or interfacing with some of these other pre-existing tools. Some things that there's a number of tools that look at leveraging hardware. So we have a shader-based volume rendering system we call VL3 at Argonne that we developed that takes advantage of the GPU and does hardware-accelerated shader-based rendering. There's some analysis environments like MATLAB and R are available for doing analysis. And some utilities for doing both plotting and manipulating images and that sort of thing. And so there's all sorts of tools that are available that are out there. I'm going to take a little bit of a closer look at some of them and compare a little bit. ParaView and Visit, as I mentioned, we're going to talk about that a little bit more today and do some hands-on stuff. But just at the high level, these are general purpose visualization applications, so they're primarily GUI-based, although they are also scriptable, so you can, generally how they're used is you use the GUI-based interactions to build up your pipelines, do data exploration, and then once you find out sort of what you're looking for, and now you want to go and visualize a time series of data, for example, then you can script that and run it, send it off and render things in batch mode. It's also extendable so that if you have, for example, a data format that's not currently supported, or if you have a specific type of filter or transformation that you want to do on the data that's not natively available in the applications, you can write your own. They're largely built on top of VTK, and they have different interface. There's Python and C++ bindings for enabling some of this extensible and scriptable stuff. As I mentioned, they're built largely on VTK, which is more of a programming environment API. So you'd use this for building up your own applications, or again, adding additional capabilities. It gives you finer control of finer control of the library. Like I said, the Visit and ParaView tools are built on top of VTK, but they don't expose all of its capabilities. So if you need something that's more, that you have finer control over, but of course, the trade-off is it requires more expertise in order to build these types of custom applications. So here's a list of, but not by any means an exhaustive list, but a list of some of the data file formats that are supported in Visit and ParaView. And so typically when you're running your simulation on the compute resource, your data format it's typically optimized for the simulation, right? So you want to take the best advantage of the hardware of the application as you can, and that format is usually very different from the format that you need the data to be in order to do visualization. So that's one of the big things that I find myself doing as a viz expert is helping people to translate their data from their simulation format to one that's going to be supported by some of these visualization tools. But like I said, there's a pretty extensive list. So there's a pretty good chance that these tools already support the data formats that you're using. But if not, there's some ways to navigate that. So I mentioned we do spend a lot of my time doing sort of data wrangling, right, doing these sort of conversions. So XDMF is a pretty powerful format for that. It's essentially an XML wrapper around HDF5. So you can store your data in HDF5, which a lot of simulation applications do. And then you can have this XML wrapper around it. It's essentially a higher level abstraction that then the visualization applications can get access to this HDF5 data. There's also an API for that, so you could use it for the API directly from simulation applications in order to write out data in this format. which again is sort of HDF5 at the base level, but has this XML wrapper for describing it so that it makes it easier for the visualization applications and others to manipulate it. Of course, you could also write your own using, for example, VTK, which again is one of the primary formats supported by some of these Viz applications. So you could add VTK libraries to your own code, or you could write small utilities that convert data, either using your own routines or write VTK data structures out. And again, there's C++ and Python bindings for all of these. So a little bit about data organization. So I mentioned there's all kinds of different formats. And so using some existing tools that support many flavors, you can, a lot of the tools already, again, support a lot of different file formats. So options are to use one of those, or to write your own converter, or write a custom reader for an existing tool, for example. Or you could write your own custom Viz tool that, if you have a format for your data that's optimized for the way you're doing your simulation and optimized the I/O performance to write to disk a particular way, you could either, then use those same, use your own codes to load that data back into a visualization application, either by creating a plugin for one of the existing tools or writing your own tool. Say a little bit about sort of serial versus parallel or partitioned. So when you're writing data at scale, you've probably learned a lot about this already this week, that a single big file is often too cumbersome, but if you have a large-scale simulation that's running on 100,000 processors, you probably don't want every single rank of that simulation to be spitting out a file and having huge numbers of files. So there's probably some middle ground that's generally the best solution for that in terms of optimizing there. So there's a number of VTK data types that will support that. XDMF again for HDF5 and Visit and ParaView, or you can write some custom I/O for managing partitioning data and making it such that you have not one single file, but some manageable number of smaller files that contain your data in order to optimize not only performance for I/O, but also for some of the subsequent calculations you're going to do, right? Because in addition to visualization is more than just producing the pictures, but analyzing the data, running filters against it. So largely what we're doing in visualization is looking at attributes of the data and representing them as some graphical attribute. And I'll talk a little bit more about that on the next slide, or the next section. A little bit more about data organization, just an example of serial versus parallel, some of the trade-offs, in particular in performance. And this might be a little dated, but there's and different readers for different data types within VTK and ParaView have, depends on how each individual reader was implemented, but in general, serial files are generally read on the head node and then partitioned and distributed if the data is not already partitioned initially. And so as one example, I had a data set that was unstructured grid, about just under 4 gigabytes. But when I tried to run it on 64 processes of a visualization, across 64 nodes in a parallel server, it took more than 15 minutes to load the data, and majority of that was spent in partitioning and redistributing the data. But once I did that, I then saved it as a partitioned file, so now I've got 64 chunks instead of a single big file. And then subsequently, when I read in that partition data, I can do that in under a second. You end up with a little bit larger of a data footprint because there's some ghost cells and other things, some amount of redundant data in terms of of doing that partitioning, but it makes processing going much quicker. In addition, as I mentioned, some of the filters, for example, in this particular case, I was doing some streamline, and I'll talk a little bit more about that in a second, but calculating some streamlines, and those were, the performance for calculating those was sped up considerably when the data was already partitioned. All right, so I'm going to quickly walk through some data representations, some examples of some of the types of visualization you can do with different types of data. As I mentioned, one of the primary goals of visualization, right, is to take different, we're trying to provide insight into what's going on in your data. And so trying to find ways to graphically represent different attributes in your data. So this is an example of a process called volume rendering. So essentially you have a volume full of data values, and you cast rays into that volume. And for every value in your data volume, you assign some color and opacity value to every value in the data set. And so, for example, our little mouse friend here, or rodent, whatever that is, you can assign different ranges of colors to different values in the data set. So for example, this yellow region, it must be bone. The red regions are some other sort of muscle tissue. And so you can assign different ranges of colors to different ranges of values in order to represent and segment them and represent them. Glyphs, again, so taking a 2D or 3D geometric object to represent point data. And so in this case, we're looking at using a glyph, which is just some small either 2D or 3D geographic thing. Most of these examples use spheres, but there's a couple examples here, so arrows. And again, you're trying to find ways to represent the data visually, right? So we have a bunch of arrows that are based on some vector, right? And so their orientation is based on the orientation in this example flow field, or for example, the top right image is from a simulation of fuel injection, and so the size of the sphere has to do with the amount of particles in that a particular sphere represents. It's also colored by, I think in this case, velocity or something. So again, taking different graphical attributes and assigning them to different attributes in your data. Isosurfaces or contours, another representation. So in 2D, this would be a line. 3D would be a surface. So essentially, it's a surface or a line that represents a constant value in the data set. So the point at which it's a threshold at which that value gets crossed in your data. And so Visit and ParaView are both really good at this. VTK, again, it's the same, but it requires more effort. So cutting planes, another example, which is essentially just what it sounds like. It's a slice or plane that cuts through the data set and then samples the data values at every vertex in the data set where that plane cuts through. Again, ParaView and Visit both good at this. VMD has some similar capabilities for some data formats. And again, you'll see examples of how to do this in the various tools later today. So Streamlines I mentioned a bit ago. So these are examples from a flow field that's on a mesh. It needs some connectivity in order to do this, but basically shows the direction an element would travel at any point in time. So you start with some number of seed points, and you find where the value is at that vector, and you trace along that vector to the next point in the mesh, and then so on. And so it creates these streams that represent how the data is flowing within a single time step. There's a similar representation of path lines, which is more time dependent. So you would follow the path of particles from one time step to the next. In this case, it's within a single time step. So I mentioned there's some tools that are more specific for particular science domains. So VMD is an example of that. And again, John is here to talk about that later today. So there's lots of domain-specific types of representations, ball and stick types of things. But right, so it's scriptable. You can create animations with it. Visit and ParaView have limited support for these types, but that's improving over the years. And I know that they've added some recently. There's a VTK molecular representation. And again, VTK, anything's possible if you try hard enough. But again, it takes some additional experience and expertise to dive in at that level. The last couple of slides before I turn it over to Silvio, who's going to talk about the in situ stuff, about annotation, using some tools for doing annotation in movie creation. So in particular, this is an example of a command line for image magic, which is, and it's not meant to scare you, but just to sort of show the power of how you can do some pretty powerful things using these command line tools. So what this is doing is, and you'll see the result of it in a second, is essentially I've got 4 images that I want to composite together. Each of them has a color scale and a different data range. And so sort of break this down into here's one chunk, here's another chunk, here's the 4 different pieces. I guess the top part was combining the images, the rest of them were adding the annotations, and then this is the resulting image from that. So again, I didn't expect you to read all that and understand the details of it, but just to show it's pretty powerful in terms of a command line tool for enabling you to combine these types of, combining multiple images and annotations and putting it all together. Now, some of the visualization packages enable you to do some level of that too. I find that I tend to do things sort of in stages, right? And I might want to repurpose some of the images I make for different things. So I tend to generate the images first, and then I'll add annotations to it so that, in one instance, I might want to annotate it one way. I might want to combine things a different way. And so rather than have to go back and re-render everything again, I have my a stack of rendered images that I'll do some scripting and apply various annotations and stuff to. And this is just another example of doing some manipulation of multiple images. And I thought I found, I have an animation of this, which I thought was in here, but I guess it's not. Where we show zooming in of that region where I took essentially the final image and scaled it up and changed transparency, and that was all done using image magic. As I mentioned, most of the tools enable you to spit out a movie as an AVI or some other encoded movie format. And that's great and easy for something quick. Again, I tend to, but you can also spit out individual images. And I tend to go that route because it gives me more control, right? So I can combine them into different segments and do different things with them later. And then one maybe handy shortcut so FFmpeg is a movie encoding framework. And so it's as simple as a single command line to combine a stack of frames into a movie. But I've found that if I'm building up movies in different segments, FFmpeg likes to have one big long pile, one big list of images. And so what I'll generally do is if I have them created in sort of segments that live in different directories, I'll write a little script that combines them and makes a list of symbolic links to each of those images in order so that I don't have to make multiple copies and manipulate them that way. It's just a sort of a handy way of organizing and curating the piles of images. So I mentioned that oftentimes visualization, the final product isn't always the end goal. So here's a couple of examples of using visualization in debugging. So in this particular case, this is an example of the simulation is fluid flow past these two propellers. These are marine propellers, and they're rotating in opposite directions. And so I was working with the team that was doing this simulation, and the results were, they weren't understanding the results. Something was wrong, and so they asked me to help out. And so in this case, the flow is going from right to left. And pay attention to what happens to this propeller. And the one on the right is the one in the front. So as the simulation goes on and these propellers are turning, at some point, the first one went away. So as you can imagine, the results were very different than if there were two propellers. And so it turned out that they had a bug in their code. Something wasn't reinitializing that caused that first propeller to go away. But they had no idea what was going on in the code until we did this visualization. So this is sort of a success story of how visualization can help shed light on what's going on in your data, in your simulation. So now this is an example of what they were expecting to see. Again, you kind of see inside here the little white region. You can see the propeller a little bit. And so they were expecting to see these vortices as the simulation went on, but they weren't in their case because, as you saw, they had the broken propeller. And then here's one more quick example of, I mentioned we have our own volume rendering software, and we were trying to add some parallelization and do some threading on it. And we weren't getting quite the performance we were expecting. And so in an effort to try and understand how the threading was working and how memory was laid out, so normally what we would do is we'd cast an array and look at the value that's in the data, right? So you see these clumps where there's these bright spots where there's high concentrations of galaxies in this case. But instead of looking at the data that was in the data set, we colored it by the thread that was doing the processing. So by doing that, depending on how we laid out the threading, it looks very different, right? And so, and in this case, I don't remember which one was the optimal, but you can see that the patterns are very different. And so this helped shed some light on what processes and what threads were operating on which parts of the data. And so again, another sort of diagnostic way of using visualization for doing diagnostics and understanding what's happening in the simulation. That wasn't the end result of the data, but it helped shed light on performance of the simulation, or in this case, the visualization. So at this point, I'm going to turn it over to Silvio Rizzi, who's also from Argonne on my visualization team, to talk about in situ visualization and analysis.
So hi everyone. I think I've met most of you last Saturday during the tour. But again, my name is Silvio Rizzi. I'm a computer scientist at the Argonne Leadership Computing Facility. And I work with, I'm part of the team, the visualization and analysis team with Joe Insley and Mike Papka, who will be also speaking later today. And so what we want to do with this brief introduction to in situ visualization and analysis is just give you an overview of things that we will need to do in the future, especially in preparation for exascale. So we would like to show you quickly the things that we're doing, the things that we're investigating, and also give you this brief overview so that you know what things are available and at some point, you may be able to use them too, or you may need to use them too. Okay? So in terms of in situ visualization of analysis, you will read and hear in multiple places that it's kind of unavoidable. The thing is that the CPU processing and the flops are continuously increasing, but the I/O is not, and the gap is actually increasing. So what we're currently doing in most of our large-scale simulations is just dumping data at a specific rate, right? So if there's if you're computing maybe 1,000 time steps, you may be able to afford only dumping to disk a fraction of that because of the time it takes and because of storage limitations, right? So an alternative way of doing things would be to process and to do the analysis and eventually visualization while the data is in memory, while the data is available, right? So that's essentially in situ. And there's multiple variations of that, but that's in a very concise way, or in a very short way, description of it. So what are we doing? How are we trying to solve these problems? There are existing in situ infrastructures, right? Well-known in situ infrastructures. Catalyst from the ParaView team, from the KitWare team. LiveSim from the Visit team, and Adios, which I think it's living in Oak Ridge these days. So there is this well-known infrastructures, okay? We're trying to use them. We're trying to combine them and take advantage of them. So these are the questions, right? Can we enable the use of any of these frameworks or any others? Or can we try to develop our analysis in a way that is portable, right? And also, the question is not here, but for that, we will need specific data, data format, right? So, or data model. So it is here, actually. We propose a data model to pass data between simulation and analysis. And as you will see, this is based on VTK, the Visualization Toolkit. The Visualization Toolkit, it's been around for a couple decades now. And the data structures that they provide can be reused in this, for this specific applications, right? And we also want to propose an API for instrumenting applications. So if you want to instrument a simulation, right, you will need to add some code to it. So we want to minimize the modifications that you need to provide to your application, to your simulation code, in order to enable in situ. And this is the name of our project. Our project is called Sensei in situ. It's funded by DOE, the Department of Energy. And we work with colleagues from Oak Ridge National Lab, from Berkeley, and companies like KitWare and Intelligent Light. So the data model, as I anticipated, is based on VTK, the Visualization Toolkit. And there's an advantage there because ParaView and Visit are essentially based on VTK. So it simplifies things. And also, one of the main advantages of it in recent versions of VTK is that it enables zero copy. This data structures, right, are good when you don't want to copy data. Imagine that you're simulating data and your data is actually really large, right? You want to minimize copies of that. Using this data structures, you can pass pointers around and minimize or actually avoid copying data. So that is essentially what it looks like, right? So you have your simulation. it is instrumented with Sensei and the VDK data model, and you could provide that data to multiple analysis algorithms, and they all should be able to understand that. So there's one advantage there. We use a single data format that you can understand from multiple analysis algorithms. And this is what the actual architecture looks like, right? So this is your simulator, your simulation. You need to create a data adapter and a bridge, and the bridge will communicate the data with the analysis adapter and multiple analysis algorithms. So the structure is really simple. So what you do to instrument simulation? Essentially, write the data adapter, and that is simple to do. And actually, the framework provides some mini apps that you can take as examples. So it's actually easy to do. And then you write the bridge, and the bridge will define the communication, right? When the simulation finishes computing a time step, it will call the bridge, and the bridge will inform the simulation that new data is available. On the analysis side, well, you write the analysis adapter, and it will understand the VTK data coming in, and then it will do whatever is needed to the data. So this is just, here we're trying to show how simple it is to instrument an existing code, okay? So this particular example, 13 lines of CMake code changes in order to reconfigure stuff, 18 lines of C++ code needed in your simulation, and whatever you're going to do, whatever kind of analysis you're going to perform on this can be specified in an XML file. And the XML file looks like this, right? So in this case, we're saying, hey, I got data. Please pass it to Catalyst, run a Python script, and this is the file name. So data from the simulation will come to Catalyst directly, and it will execute whatever is in that script. After that, you could perform, this is kind of a custom code, autocorrelation, right? And then you could pass it to Adios, and Adios will write it to this file name. It will dump the data into this file name using its MPI method, and so on. So you can see how simple it is to combine multiple in situ infrastructures just by using or specifying what you're going to do in a simple XML file. So this is what it will look like for a specific example I'm going to show. So this is a mini app that is it's called ISO, instrumented with Sensei. And on the analysis side, it is ParaView Catalyst running a Python script. So it's not readable, but that's the script, which is relatively simple, the one on the right. And this is what the XML file will look like, right? You're calling Catalyst, and you're passing this 3 extra parameters. And there's actually an example of this. You can see that this is the simulation instrumented with Catalyst. And we're going to connect it. We're going to connect Catalyst with a ParaView server, and ParaView server with ParaView client. Okay? You will see more about this in some other sessions today. But there's ParaView is actually client server. So this will run all on one of our supercomputers, Theta. And this other side, you could run on your desktop or laptop computer. Okay? So this provides all the interaction. So while the simulation is running, it is producing data. The data is going to Catalyst, and from there to ParaView server. And you're connecting your client to that, and you could interact with the data while the simulation is running. There's multiple advantages in that. One thing is to actually monitor the simulation, right? Monitor that it's doing the right thing and not burning unnecessary cycles if it's actually getting the wrong results. But you could also be extracting some data directly from ParaView while the simulation is running. So as I said, that the client will be local. And I have a video example of that. I will be doing some fast forward here because it takes too much time. But now it is connecting to the server. We're specifying the connection parameters. And now it will launch the server, the ParaView server. And this is the part that takes time, so we'll be fast forwarding. By the way, this video is from Andy Bauer at ParaView, and he shared that with us. We work as part of the same team, so it's all. I should mention him. So his work. So now we are connected. And at that point, we're actually receiving data. Now you can see from the ParaView client, it's showing a render view, right? And it's getting, you will see in the ParaView talks today how these things are called filters and how you can use multiple of them, connecting them like a pipeline. So that is essentially what we're doing here. And we are processing the data on our desktop that is actually coming from the simulation, from a live simulation. And that's the point we wanted to illustrate mainly with this brief introduction. Okay? So you can see that you can process or do multiple operations to the data, maybe extract isosurfaces or filter the data somehow. And this is other different processing operations. But you get the idea, right? So that's the key points we wanted to illustrate. I need to mention again our project and the slides coming from Andy. So thanks to Andy and the rest of the team. And with that, we'll be happy to take any questions you may have. We actually have a lot of time, so yes.
So how does it work with respect to the memory so that the simulation can continue while, for example, very extensive visualization scripts are running? Is there a copy being made, or can the data be transferred off to the GPUs and then processed there independently? Or what is the memory model below?
Right. So the question is, what happens with the memory, right? If the simulation can proceed while we're doing analysis. It depends. If you create a copy, if the simulation needs the data, you will need to create a copy. But that is expensive, right? But sometimes you can afford like maybe 5% of your total simulation time devoted to analysis, right? In that case, you may not need to copy the data, and you could do the analysis and visualization, right? So it depends. There's another possibility too. You could copy the data to a different partition of the machine, right? So you could have your simulation running on maybe 90% of your machine, and the analysis running on a 10% of your machine. But that may need copying the data. If you can afford that, that's good, and your simulation can proceed.
Possible within the Sensei interface?
It is, yes. It is actually really simple, and I don't know if I provided the link, but the code is online. Yeah. If you go to this link, there will be a link to the Kitware repository, and you can get the code and look at that. It's actually really simple. And it's open to modifications, right? So one thing, for example, one of the things I'm doing now is adding a different infrastructure, an additional infrastructure, and that is relatively simple to do. Other questions for me or Joe?
Like, to run this, both have to be run on the same machine. Can it be like I'm running my simulation on Mira, and then I do my analysis on Cooley?
Correct. So the question is if we need to run on the same machine or we could ship the data to a different machine. Yes, both, actually. In situ is, well, there's some debate about what in situ is. But traditionally, it means that your compute nodes are also doing analysis, right? But there's another way of doing it. Some people call it in transit, where you move the data to a different resource. And yes, Cooley actually was designed for doing these things, this kind of things, moving the data from the simulation to the analysis resource. So yes, and it is possible to do with Sensei. Other questions?
So I may have missed this, but do you need to integrate, like, for example, Catalyst into the code, or just Sensei and then write a Catalyst script separately and then have everything work?
Sensei may need the Catalyst libraries if you're using Catalyst. Yes, you will need to build libraries, extra libraries like LiveSim or Catalyst or Adios.
Link them into my code.
And link them, yes. Right. There's other ways of doing it. So for example,
That's on the analysis side,
that's, yeah,
not necessarily on the simulation side.
correct. And that's what
So
I'm
I
doing.
don't need to instrument my code necessarily with Catalyst.
Your code actually you will need to write the bridge that I talked about, and the bridge will need to understand VTK format, the VTK data, in order to encapsulate the data. That's all what you will need on the application side. One of the things that I'm doing now is working with a code called LAMPS. You may know it. And it's possible to drive it as a library. So in that case, I don't need to touch it. I'm writing my own driver, which talks to Sensei, but LAMPS doesn't need to know about that. Any other questions? Questions about this? All right. Thank you then.